Hello students, Straight here. This little video you're going to be taking notes for section 11.1, distance and displacement. As you get done taking the notes, you'll submit them through Google Classroom. Here we have a video of a person trying to catch a butterfly, and questions that could be asked. How fast is the butterfly moving? What direction is it moving? To describe motion, we must state the direction the object is moving as well as how fast the object is moving. You also need to tell the location at a certain time. One of the key questions, what is needed to describe motion completely? To describe motion completely and accurately, a frame of reference is necessary. Our definition for the frame of reference: system of objects that are not moving with respect to one another. You may want to pause this video at any time you need to finish writing down the highlighted material and then start it up again. We're looking at a train. How fast passengers are on the train or moving depends on the frame of reference to measure their motion. Relative motion, key concept we'll be looking at, movement in relationship to a frame of reference. As the train moves past the platform, the people standing on the platform will see those on the train speeding by. But when people on the train look at one another, they don't seem to be moving at all. When we use the term motion in physics, it means always will mean relative motion in relationship to a frame of reference. All objects are constantly in motion because the Earth is constantly in motion. So if we could look at an object up from outer space and see it, it would appear to be moving because the Earth is moving. But we're always going to be concerned with relative motion. Someone on a speeding train, others on the train don't seem to be moving at all. If you sit on a train, look out a window, treetop might help you decide how fast you're moving. If you get up and walk towards the rear of the train, looking at the seat or the floor shows how fast you are walking relative to the train. Choosing a meaningful frame of reference will allow you to describe motion clear and relevant manner. So we have to choose appropriate frames of reference. Then we move into a thing we call distance and displacement. Two similar things, but slightly different. Distance, length of a path between 2 points. So the path traveled affects the distance. Distance is what we call a scalar. And we'll be using these terms as we continue through this physics unit. So scalar, things like distance are a scalar. Displacement includes the direction from the starting point and the length of a straight line path from the starting point to the end point. Displacement is what we call a vector. V-E-C-T-O-R, vector. Vectors will always have a direction with them, and most things we talk about in study of motion have a scalar component and have a vector component. So distance, the length of the path between 2 points. When an object moves in a straight line, the distance is the length of the line connecting the object's starting point and its ending point. SI unit for measuring distance is the meter. For really big differences, we might use the kilometer. For smaller distances, we might use the centimeter. We also use bigger units like a megameter, smaller units like a picometer. To describe an object's position relative to a given point, you need to know how far away that is and what direction it is. Displacement provides that information, both something about a distance and a direction. Got a motion of a roller coaster car. Length of the path which the car has traveled is the distance. Displacement is the direction from the starting point of the car and the length of the straight line between them. After completing a trip around the track, the car's displacement is 0. If you went out on the track to high school and you ran around the track once, your distance ran would be approximately 400 meters. Your displacement would be 0. Because you're back where you started. So distance and displacement can be completely different numbers. And if we want to add displacements, we're going to add displacements using what we call vector addition. And a vector, and as I mentioned earlier, a quantity that has both magnitude, that's the number part, and the direction. Direction can be specified in many ways, like north, south, east, west. I use degrees. I talk about a 20-degree angle, displacement of 20 degrees. We can talk about just forward or backwards. So a lot of different terms that will help us to describe direction. Displacement, as mentioned earlier, is a vector. The magnitude might be a size, a length, or some amount, the numerical part. We use arrows on a graph or map often to represent vectors. Length of the arrow shows the magnitude of the vector. And we use a process we call vector addition to combine these vectors together. So if two displacements have the same direction, you simply add the magnitudes. If they're in opposite directions, you subtract the magnitudes. So same direction, opposite directions end up being fairly simple to deal with, as in this little diagram here. We got two vectors, 4 kilometers, 2 kilometers going in the same direction, so we add the 4 and 2 and we get 6. 6 kilometers, and here we could just say forward. Now they go in the opposite direction. We take the 4 kilometers, subtract the 2 kilometers, and our result, we call the resultant displacement, ends up being 2 kilometers. So adding or subtracting. So when things are in the same or opposite direction, rather simple to figure out what we call the resultant displacement. Now, they have different directions. Then we're going to combine them by graphing. This will be a part we won't deal with too much other than just mention it here. I will expect you to be able to add, subtract, combine vectors when they are in the same direction or opposite directions, like on the preceding slide. This one, I'd expect you to be able to get a general approximation of how far it is. If we took out graph paper, draw them, we could be pretty fairly accurate with them. And in class, we probably will have you try one of these in class. So with these next few slides, we've got the resultant vector is going to be the diagonal red line, and the actual distance is represented in yellow here. So the boy went 1 block east and 1 block north. Then he goes a couple blocks back east and goes 3 blocks back north to get to the school. So if we add up all those things, that's going to be his distance traveled. So that'd be 1 and 1's 2, and 2 is 4, and 3 would be 7. So the child walked 7 blocks to school. That would be the distance. But the displacement is this red arrow. And it ends up being about 5 blocks. And then to get an accurate displacement, we would give it some type of a direction. Here we could call it northeast. If we wanted a more precise, we add a degree measure in there. So, boy walked a total of 7 blocks, some of the magnitudes of each direction. The vector in red was called the resultant vector, a term I used a while ago. The resultant vector, vector sum of 2 or more vectors. The resultant vector always points directly from the starting point to the ending point. I get a few review questions. Pause the video, read the question, try to answer it, and then come back and see if you did it correctly. Write down whatever will be useful to you in your notes on these questions. So, question 1 here. We got a car driving down the highway. Which frame of reference does it appear not to be moving? Standing on the side of the road, car driving the same speed but going in the opposite direction, sitting inside the car, or an airplane flying overhead. The correct answer ends up being C, sitting in the car. If you're sitting in the car and you're just looking at something in the car, you're looking down at the floor of the car, it doesn't look like the floor of the car is moving, or you're looking, if you're in the back seat, look at the seat ahead of you, it doesn't appear to be moving. But all the other ones, if you're standing on the side of the road, it's going to appear to be moving. The car, you can see it going down the road. If you're in a car traveling at the same speed but going in opposite directions, sure, it's going to appear to be moving. It's going to come towards you, go away from you. Now, there would be one if you were in a different car traveling at the exact same speed and you just focused on the other car, then it would not appear to be moving. If you were going in the same direction but going in opposite directions, it's going to appear to be moving. And an airplane flying overhead. An airplane looking down at the car, definitely see it moving. So again, C, our correct answer. SI unit distance would be most appropriate for measuring the distance between 2 cities. So we got a meter, a centimeter, kilometer, or a mile. And our best answer there is going to be the kilometer. Meter and a centimeter are going to be too small. A mile is not SI. So no mile, no centimeter, no meter, but a kilometer. About appropriate size distance in the SI for measuring between 2 cities. We could use the other ones, but they're not the most appropriate things. So if you walk across town, Taking many turns, your displacement is total distance you traveled, distance and direction, your straight line, starting point to end point, distance in a straight line from your starting point to your ending point, or the direction from your starting point to your ending point. And the correct answer here would be B. We're talking displacement. We must have both distance and direction. So not just distance like on A, not just distance like on C, or not just direction like on D. It has to be both a distance and direction, and it has to be in a straight line from your starting point to your ending point. So the other ones are only part of what we need to have a correct displacement. And if you travel 30 miles west of your home and turn around and start going back home after traveling 10 miles east, what is your displacement? So we got 20 miles, or 20 kilometers, or 20 kilometers west, 40 kilometers, or 40 kilometers west. Here, answer is B, 20 kilometers west. A and C would be automatically eliminated because we're trying to find a displacement, and a displacement always has to have a direction. And the displacement, so 20 and 40 kilometers can't be right, and they were in opposite directions. One of them was going west, the other one was going east, so we end up subtracting 30 minus 10 to get to 20. If they were going in the same direction, then the 40 kilometers west would have been the correct answer. But because they're opposite directions, we needed to subtract. So that completes our little video for section 11.1, distance and displacement. Should have some nice notes for it. Now, make sure you submit this through Google Classroom.